A Poisson distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval. The random variable x is the number of occurrences of the event in an interval, and the interval can be time, distance, area, volume, or some similar unit. The probability of the given event occurring x times over the interval is given by our equation. The probability of x is equal to the mean to the power of x times e to the power of negative mean, all divided by our x factorial. Some examples of where this could be used would be things such as radioactive decay, the arrivals of people at a location, the number of eagles in a specific location, the number of car crashes in a year. As a note, the value E is approximately 2.71828. It continues on. And there's a button on your calculator to use when you need to use it within your calculation. How do we determine if something is a Poisson distribution? The biggest thing is that it has to be a random variable, and the number of occurrences of the event occur over some interval. In addition to that, those occurrences must be random, they must be independent of each other, and they must be uniformly distributed over the interval. We can find, in addition to the probability of a Poisson distribution, we can find the mean and the standard deviation. The mean is going to be the total number of items or the total number of events divided by the interval. And the way that we find the standard deviation is we take our mean and we take the square root of it. We're going to look at an example. It says here, for a recent period of 100 years, there were 93 major earthquakes, measuring at least 6.0 on the Richter scale in the world. Assume that the Poisson distribution is a suitable model. Find the mean number of major earthquakes. Well, we need to know the number of items and divide it by the interval. The number of items or occurrences in this case was 93. And the interval was 100 years. So the mean is going to be 93 over 100, or 0.93. Now, if we wanted to find the standard deviation, all we would have to do is take the square root. The standard deviation would be equal to the square root of 0.93, or 0.96. So kind of as a side note there. The big thing that Poisson distributions can be useful for is finding probability. So if the probability of x is the probability of x earthquakes in a randomly selected year, find the probability of 0 earthquakes, 3 earthquakes, or 7 earthquakes. All we are going to need to do is apply our Poisson formula. The probability of 0 earthquakes is going to be equal to our mean, which we found in part A to be 0.93, to the power of x, here our x is 0, times e to the power of negative 0.93, or negative of the mean, divided by our x value factorial. And then all we have to do is substitute and use a calculator. Now, anything to the power of 0 is 1, and 0 factorial is 1. So for this problem, all we really have to find is what is e to the power of negative 0.93. And we get 0.395. The probability of 0 earthquakes is 0.395. The probability of 3 earthquakes will be 0.93 to the third power times e to the power of negative 0.93 divided by 3 factorial. Use our calculator. 0.93 to the power of 3 times e to the power of negative 0.93 and divide that by 3 factorial, and we end up with 0.0529. The probability of having 3 earthquakes in a randomly selected year is 0.0529. And then we would do the same thing for 7. The probability of 7 earthquakes is going to be 0.93 to the 7th power times e to the power of negative 0.93 divided by 7 factorial. And we end up with 0.0000471. So the big thing for Poisson distributions is that they have to be over some interval, whether that interval is time, distance, area, etc.